So, in this lecture we continue with a discussion on design styles in VLSI. If you recall, in our last lecture we had been talking about the FPGA field programmable gate array design style and what are its specific features and rules during the design. Now, we continue our discussion in that line. So, the first design style that we will be talking about today is something called gate array. Now, gate array is something that comes right after FPGA. See, the two extremes of the spectrum are FPGA on one side and a pure ASIC on the other side. Now, you recall what we had said. So, when you want to manufacture an ASIC, we have to send our design to the fabrication facility. They will be carrying out all the steps of fabrication, they will be manufacturing the chip and they will be sending it back to us. But on the other extreme, we have the so called field programmable gate array or FPGA, where the entire programming and customization can be done by the user in the lab. Okay. So, the turnaround time is extremely fast. The FPGA kits, as I said, will cost you not more than few thousands of rupees, at least the simpler ones. So, it is very cheap, very fast, and you can very quickly map some design into a hardware. Okay. Now, in that spectrum, gate array is something which falls between the two extremes. I mean, you may say it is a little closer to FPGA. Okay. So, let us see the salient features. Now, the main difference from FPGA is that you see FPGA, the design customization, which we sometimes call programming, is entirely done by the user. But for the gate array, it is a two-step process. User is not doing well. Here again we are sending it to the fabrication facility, to the fab, but the effort is much less. Why? We shall explain. So, for gate array implementation, we actually require a two-step manufacturing process. So, when we say manufacturing, that means we are trying to build something. Now, in a gate array chip which will ultimately implement or realize some functionality, there are two steps. First step is independent of the function being realized, and the second step is a step of customization. So, you see, in the first step you can complete the first step for all the designs irrespective of what is the function you want to implement. And once you have done that, for specific designs you will have to separately carry out step 2. Okay. So, the first phase which I am saying, this is based on some generic masks during fabrication. So, actually what we are doing here, we are actually fabricating a large number of transistors on the chip, but what we are doing, we are not interconnecting the transistors, we are simply fabricating a large number of transistors, which is the first phase. Now, in the second phase, where you are doing the customization, we are completing the metal interconnects. We are interconnecting the transistors in a way which will help us in realizing the functionality of a circuit. Okay. These are the two phases of manufacturing. First phase is a generic step which is independent of the design, while the second step is design specific, where we carry out the interconnects, we interconnect the transistors to form gates and again interconnect the gates to form our desired functionality. Okay. So, pictorially the process will look like this. Now, in the first step, which is shown on top, so you simply create a large number of transistors using standard masks. So, what we get is a number of silicon wafers where the same large array of transistors are fabricated. Now, you see, when you are fabricating something in a fab, it will cost you money. So, when you are fabricating in millions, your means your total cost will be distributed or divided among the number of items you are manufacturing. So, because we are manufacturing these base wafers in large numbers, the total cost of the first step is getting distributed among all these designs, so that the per design cost of step 1 becomes very less. Second step is the actual customization, where you complete the metal interconnections. So, the transistors which are fabricated, you interconnect them in some way, right. So, after this you get your final design. So, some features of this design style. Number 1, because we are manipulating or working at the level of transistors, clearly the chip utilization factor will be much higher as compared to FPGA. Because in FPGA chip, in the field programmable gate array, if you recall, there was something called configuration logic block, the CLBs. Now, inside CLBs there were the lookup tables or LUTs. Now there, apart from the LUTs, there were a large number of other circuitries as well, lot of multiplexers, some flip flops, whether you need them or not, those circuits are also there. So, maybe out of that you are utilizing only 60% or 70% of the hardware, the rest you are not actually using. Okay. So, in that respect, when you go for this gate array kind of design style, where you are working at a much lower level, at the level of transistors, so you can just utilize the transistors in a much better way. So, wastage will be very less here. Okay. And because you are working at a much lower level, your chip speed in general will also be much higher, okay, because the delay will be less, because all those complicated circuitry as there in FPGA, they will not be there in gate array style. So, a typical gate array chip can implement millions of logic gates or even more. Okay. So, this is the idea. So, next let us move on to a standard cell based design style. Now, standard cell is one way to implement ASICs. So, under ASIC, what we are trying to say is that when we talk about application specific integrated circuit or ASIC, there are two broad ways of going about the manufacturing. One is called standard cell based. This is sometimes also called semi custom, and the other alternate style is full custom. Okay. These are the two broad approaches. Now, in these approaches, the basic idea is that you have to go through all the steps of fabrication. So, your fabrication cost is not changing, right. So, what is changing will be your design cost. Now, in case of standard cell, you are using some pre-designed cells from the library, you are picking them up and putting them in your designs. That is your standard cell or semi-custom design. Whereas, for full custom design, you are theoretically designing everything from scratch. So, naturally it will take much long time to design a reasonably complex circuit. Okay. So, let us see the features of the standard cell based design style. So, this is one of the most widely used design style for manufacturing ASICs today. So, as I said, this is also called semi custom because it is not full custom. Lot of the design cells are already pre-designed and available to us, we are reusing them. But as I said, we have to go through all these steps of fabrication, which means we have to develop the full set of masks that are required for fabrication. So, the basic idea, as I said, that you use some simple logic cell which are very commonly used and store them in a library which is typically called the standard cell library. Now, when we store them in the library, actually what we store is a highly optimized layout. So, it is not that it is a gate level netlist, we are taking the gate level netlist, putting it on our design and later on we will be thinking about layout, not exactly that. We are getting the layout directly, you can put it straight onto silicon, okay? That is the idea. So, the typical library for standard cell may contain few hundred cells. So, cells may contain simple gates like inverters, NAND, NOR, or more complex gates like AND or invert, OR and invert, multiplexer, latches, flip flop, these kind of cells. Okay. Fine. Now, there is something very unique about these cells. The cells are designed with a fixed height, but their widths may be different. So, the idea is as follows, I am just trying to show you. Suppose I have a cell like this, which geometrically has a shape of this form. Let us say I have another cell which has the same height, but width is different. There is another cell, same height, but the width is again different. So, when we put these cells on a chip, suppose this is our final chip. So, here we place all the cells in some well defined rows. Suppose this is one row, the height of a row will be equal to the height of this cell, and within a row what we do? We just place the cells one after the other, they will be physically touching each other, right, like this. So, you see the layout also becomes very regular, all the cells will be arranged in terms of rows. So, some more cells will be placed here, there will be some cell here and so on. So, in standard cell the layout looks something like this, very regular, where everything is placed in terms of rows. Okay. So, in terms of the design, in terms of the routing, in terms of the floor planning, the task of the designer becomes much simpler here, right. So, just as it said, each cell is designed with a fixed height. The power and ground rails, the lines run parallel to the upper and lower boundary. I will just show an example shortly. The reason is that if you just connect two of the adjacent cells side by side, if you just connect them together, the power line VCC line will also, VDD line will touch and also the ground line will touch. So, you will be getting continuous signal for the supplies, power supplies, and typically the input and output pins are located on the upper and lower boundaries. Let us take an example. So, here I am showing an example of a layout. Well, this is a way in which we show a layout. This is called a stick diagram. So, the blue lines are the metal connections, red lines are the polysilicon connections, green and brown are the diffusions, here are the N type transistor, here are the P type transistor, and this black crosses are these are interconnections. So, you see here we have implemented two gates, one NAND gate, one NOT gate. This part is the NAND gate, this part is the NOT gate. There are two inputs A, B. So, you see the inputs A, B are available vertically here. So, the transistors that make this NAND gate, there are two transistors here and two transistors here, and this is the output of this gate. This output of the first gate feeds the input of the second inverter. There is an N transistor here, P transistor here. So, you see for both the cells, here we are showing that the two cells are touching each other. So, VDD is running on top, ground is running on bottom. So, when they are brought together and touch each other, this VDD and ground lines become continuous. So, this is just an example. Okay. Fine. So, just as I had shown you, so when you think of the floor plan of standard cells, so the chip area actually will consist of some rows of standard cells or columns, whichever way you think of. Now, the design and layout of the cells will obviously ensure that when you place them side by side, their heights will match and the neighboring cells can abut side by side. This is because of the restriction that you have imposed, that all cells have to be of the same height. Because they are of the same height, you can put the cells side by side, and within a row, any number of cells which can fit in a row, you can put them side by side just touching each other. So, the VDD will be on top, ground will be on bottom, and all the signal lines will be running vertically. Okay. They will be interconnected later on using some space which are available within the rows. Those are called channels. Okay. So, this is a typical standard cell layout which shows 3 rows. You see, this is one row, this is one row, this is one row. So, the different standard cells are shown. You see here, these are the cells, and you see some of the interconnections are shown. So, the space between the rows, this part is called channel. You see some of the interconnections are made like this. Okay. Well, it may so happen that one point here, a pin here wants to be connected or needs to be connected to a pin here. So, what do we do? You have to cross a row. So, there are some special cells also available which are called through cells. So, what it does? It simply provides a connection path from the top to bottom, nothing else. So, you can use one of such cells to make a connection from here to here and then to here, right. And the power supply and the ground lines can be fed from two sides. This is your VDD, it feeds the VDD lines, and the other side you have ground, it feeds the ground lines. So, this is a typical layout structure of a standard cell based design. So, a typical standard cell layout for a moderately complex design is shown here. These are the cells and the interconnections you see, they are quite complex, right. Fine. Now, let us come to full custom design. Now, for the standard cell or the semi custom design, what we had assumed? We had assumed that the cells are already available to us, their layouts are available, their geometries are very well defined, their heights are same, the relative vertical positions of the VDD and ground lines are the same. So, I can simply put the cells side by side. But in full custom design, we are not making any such assumption. We are saying that our basic blocks in the design can be of any arbitrary complexity, any arbitrary size. Some can be small, some can be big. You can place them into the chip area in whatever way you want. Like suppose this is your chip. So, it is possible that one block has a shape like this, one block has a shape like this, one has a shape like this, one is like this, one is like this. So, they can come in any arbitrary shapes and sizes. Okay. So, you can see that here the problem is much more difficult. Here some very important problems pertain to placement of the blocks. How to place the blocks, or in what way should I place the blocks so that my interconnection, which is called routing, becomes easier. Because say I may do one thing, I may place in such a, in one way, let us say a block A and a block B here, they have a large number of connections between them. So, all these connections have to be brought either from here or for some other direction. So, if you do not have sufficient space here for the connections, you may see that your routing fails. So, if your routing fails, you may have to go back, you may have to modify the placement and again retry. Okay. So, this is not a very easy task, this is a quite difficult task. All right. So, the standard cell based design which we had seen, this is called semi custom design. Semi because the cells that we are using those are pre-designed, but the way we are placing the cells, that is up to us, right. But in the full custom design, we are theoretically, well, no one will do it this way today, theoretically we are not using any library. So, the entire design is done from scratch, but obviously for the modern day VLSI chips, where the number of transistors can run into the order of billions, if you say that I will be doing everything from scratch, so it really becomes impractical. So, it will take you years and years to design a particular chip, right. So, as I had mentioned here, the development cost of such a design style may become prohibitively high. Therefore, all the designers today, they use a concept called design reuse. Like I am just taking an example, suppose you are coming up with a new, new design of a processor. So, you say that I am developing a new CPU, I want to manufacture it, fabricate it. So, should I design everything from scratch? Well, I may see that, well, I require a 32-bit fast multiplier, which I had already designed earlier for some other processors. So, why not I take the same design from there and use it here? This is the concept of design reuse. So, today nobody designs everything from scratch. Whatever is available, these are sometimes called IP codes, intellectual property codes. They are taken from different sources, they might be put together in a same place and you can integrate them in a suitable way. Okay? Fine. So, this is what is called design reuse, which is becoming very popular nowadays. This obviously reduces the total time for design and also the cost, they are related. Fine. So, with respect to full custom design, there is one kind of chip which always requires full custom design, that is the memory cell, because memory is the, you can say, the one design where you pack the maximum number of transistors in a chip. Well, you look at two chips side by side, one a processor, one a memory chip. In a memory chip, because the layout of the transistors, the way you are putting them are extremely regular and you have millions of such rows and columns you are using. So, the design becomes very compact. So, you can put in much more number of transistors as compared to a processor design where your layout may not be that regular. In a memory, there will be a large number of rows, a large number of columns with some transistors or some cells sitting at the junctions, very regular kind of layout, right. So, memory is one such design where full custom design is religiously practiced. So, here if you design one cell, the layout of one cell, you can simply replicate it a billion times, let us say. Okay? So, it becomes easy. But for a design like a processor where there is a lot of logic, then you can have a lot of mix and match. Some part you may implement using standard cell, some part you can have the blocks which are pre-designed, some parts you can use something called programmable logic arrays and so on. Okay. So, if you want to go for a full custom layout which is religiously you are trying to start from scratch, where orientation and placement of every transistor has to be done individually by the designer, then you think. So, statistically it has been found that the design productivity for this kind of a design philosophy is typically 10 to 20 transistors per day per designer. So, even if a company puts in 1000 engineers for this design, you just imagine for a 1 billion transistor design how long will this take, right. Because of the high labor cost and time, this is actually never done. So, memory, very high performance microprocessors like the ones Intel manufacture, for example, which are sold in millions, and FPGA chips, the masters, they are also sold in large quantities. These are some designs where you can put in some effort in order to improve their performance. Okay. So, this is just an example of a full custom layout. So, the way it looks like, you see there are different regions, they are all marked in different colors. You can see this is one regular region, this is some region where there is not much regularity, and so on. Okay. These are the I/O cells, input output cells. So, just to compare among the design styles we just now talked about, FPGA, gate array, standard cell and full custom. So, we have ordered the designs in this way, because FPGA is the easiest, full custom is the most difficult. So, we are comparing this with respect to these parameters: cell size, cell type, placement, interconnect and the total time for design. Cell size in FPGA, everything is prefabricated, right. The CLBs, the LUTs, they are fixed. Gate array also, the transistors are the cells, they are fixed. Standard cell, cells are not fixed, but their heights are fixed. But full custom, you have complete flexibility, they are variable. Cell type, in FPGA you have the LUTs, but you can implement anything by programming them. So, this is programmable. But in case of gate array, there are some gate arrays where there are a large number of NAND gates which are built. So, the cell type is also fixed, they are NAND function. But standard cell, there are various different kinds of cells, full custom also there can be different kind of cells. Cell placement in FPGA and gate array are fixed because the cells are already there. In standard cell, you have some restriction, cells can be placed along rows, but in full custom you can place them anywhere you want. Similarly, for the interconnect, for FPGA, well again this is programmable, but for the other three styles, interconnect has to be done based on the user requirement, they are variable. Design time, FPGA is very fast, full custom is the slowest, gate array is here, standard cell is here. Gate array will be of course faster than standard cell. So, this is how the whole thing works. So, with this we come to the end of this lecture. Well, over the last two lectures, this one and the previous one, we have talked about the different design styles. Well, most of you, most of the time will probably be using the FPGA based design style only, and there as the programming vehicle, you will be using some hardware description language like Verilog or VHDL as I said. There are other languages also available, many people they also use those languages. So, in our next following lectures, we shall now be moving into the details of the Verilog language, some syntax, some semantics, and we shall be illustrating them with examples, and we shall be progressing to more and more complex features and complex designs. Thank you.